Okay, so let's start off by just practicing our alkene and alkyne nomenclature. All right, so take a second to name these three compounds for me. All right, so in the interest of time, I'm sure you guys are still working, but we're going to kind of move along here. Again, just to refresh your memory about what we went over last class, we introduced these two new functional groups. Compounds with double bonds are called alkenes, and compounds with triple bonds are called alkynes, right? And we didn't really change our nomenclature rules, but we did have to add some stuff to them, right? And in particular for our two new functional groups, we have these two new endings. So if we look at our list here, alkanes we would refer to with the ane ending. Now for alkenes and alkynes, we're going to use ene for alkene and yne for alkyne, all right? We're still going to find our parent chain. In this case, it's these 1, 2, 3, 4 carbons. Okay? There's no substituents to identify in this particular molecule. We're going to number our parent chain. Right? And this was another sort of update to our rules, is that since there's this functional group in there, we're going to have to identify the location of that functional group in the name. So in this case, I'm going to still try to refer to it by the lowest number, so I'll pick this purple numbering scheme. So this would be 1, and then my parent chain with 4 carbons is a bute, right? That's 4 carbons, but since it's an alkene, it gets that ending ene. Right, so 1-butene. All right. Again, we're starting on this one, we're going to find our parent chain, but this was a pretty big update to our rule here. We said that the parent chain must include that functional group. So if I look at this molecule, it's really tempting to say that these 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons are the parent chain, because that's the longest continuous set of carbons. But again, it must contain that functional group. So I'm going to actually start counting from here. 1, 2, 3, 4, 5, 6, 7, 8, right? Fewer carbons, but it must contain that functional group. In this case, then, I'm going to identify my substituent as these 1, 2, 3, 4 carbons. Like we said, 4 carbons is bute, so this would be a butyl group. We're going to number our parent chain. Oh, whoops, skipped a carbon. 3, 4, 5, 6, 7, 8. And remember, with triple bonds, I said one of the easiest mistakes to make is to forget what I just tried to do, right? To forget to count the carbons on either side of those triple bonds. There's got to be a carbon on either side there. We draw it in that straight line, so it's easy to miss, but nonetheless, there would be 8 carbons in this parent chain. So then this would be 4 butyl, 2 octene. Oh no, I lied. Octine. Sorry. Okay. So again, major update to our rules that we're looking for our parent chain, the longest continuous set of carbons, but now we got this caveat: the longest continuous set of carbons that contains that functional group. All right. And then for this last one here, started off the same, where I'm going to identify my parent chain. 1, 2, 3, 4, 5, 6, 7 carbons. I'm going to identify my substituent, this chloro group here. I'm going to number my parent chain. I can go my 2 directions, 4, 5, 6, 7. Or go the other way, 1, 2, 3, 4, 5, 6, 7. And this was the second major update to our rules, right? The idea that when we number our parent chain, the functional group gets what's called priority, meaning we're only going to pay attention to the functional group when we pick our numbering scheme and make sure that it has the lowest possible number, right? So in this case, we're not going to pay attention to that chloro group at all. All we're looking at is that double bond and figuring out which one of these numbering schemes gives that double bond the lowest possible number. So in this case, even though the red has the chloro at 2, I'm not going to pay attention to the chloro group. I'm going to pay attention to my double bond, so I want the purple numbering scheme, because that puts it at 3, the lowest number. So this would be 6 chloro, 3, and then what's 7? Hept. So heptene. All right, so again, that's kind of how nomenclature is going to work. We got the same basic foundation, and we're just kind of adding on to it a little bit, right? Now that we have this new functional group. Okay. We talked a little bit last class about the geometry of a alkene and alkyne. Alkynes are a little bit more straightforward in geometry. They're linear. That's why we always have to draw them in these 4 carbons in a straight line. You can't kink it like this, right? Alkenes are, you don't have to draw any sort of a weird way, but we do have to consider that they're trigonal planar, meaning that all 6 of the atoms about that double bond lie in the same plane. There's something else that's very important about the geometry of these molecules that differ from our alkanes, okay? And that is that double and triple bonds cannot rotate. Single bonds are constantly rotating, right? So we draw these molecules in this like straight zigzag. They're not staying like that. They're not frozen in that zigzag conformation. They're constantly whipping themselves about, twisting all around, okay? So, for example, for an alkane, if I drew pentane, the sort of like natural default way to do it would be in this straight line here. But if instead I drew those 5 carbons, but had this last one like kinked up here, that's the exact same molecule. All I've done is rotate about this bond here, right? That sort of end group, end carbon is kind of twisting around. So these are the exact same. I can rotate about this bond, so it'd be really weird to see it written like this, but this would also just be pentane. Just kind of had those bonds rotated around, right? So although we draw them in 2D in this straight line, these alkanes aren't like frozen in place like that. They're constantly whipping about, twisting about, okay? If we get an alkene, all right, so something like this, this bond cannot rotate. Right? So what does that mean? That means that these 2 structures are different molecules. Right? Those double bonds are frozen. So the orientation of atoms about those double bonds is fixed. So these are completely different molecules. Okay. They have the same connectivity of atoms, right? I got a carbon-carbon, then a carbon-carbon double bond, right? I got the same sort of connectivity of these 4 atoms, but there's a different orientation in space. Does anybody remember what we call a pair of molecules that has the same connectivity but just a different orientation? Stereoisomers, awesome. So this is another example of stereochemistry here, right? So again, same connectivity, so this is a pair of stereoisomers. We talked about stereoisomers before with regard to like the cyclohexanes of the world, any of the cyclic molecules, okay? And do we remember what terminology we use to distinguish between stereoisomers? We put this little phrase at the beginning. What were those 2? Cis and trans. We got the same sort of concept with regard to alkenes as well, okay? So again, now talking again about these stereoisomers. Okay, we'll just use this simple example here. Okay, if you were to go and name these 2 molecules, given what we've currently learned about our naming scheme, you would arrive at the same answer, right? These are both 2 butenes. But again, when we're building our name in organic chemistry, we have to uniquely distinguish a particular molecule. So that's not going to be enough information to just say 2-butene, because I could be referring to either of these 2 molecules. Right? These are both 2-butenes. okay? So again, we're going to have that same sort of terminology that we can use. The trans isomer, just like before, means that they're pointed in opposite directions. So this would be my trans isomer here, pointed on opposite sides of the double bond. So trans 2-butene. And this would be the cis isomer on the same side. So this would be cis 2-butene. And again, we would call this a pair of stereoisomers. One thing I just want to say about your homework with regard to our previously what we discussed about stereoisomers. You had to be kind of careful when you were reading the question because it asked you to draw the stereoisomer of like cis whatever the heck it was. And it had that cis whatever in bold and so like 1,2-dimethylcyclohexane. So it was really tempting to think that that's what they wanted you to draw was cis 1,2. But they were asking for the stereoisomer of that compound. So that's why the right answer was always the opposite of what name was being displayed. All right, so just sort of two key words that if you missed would have made that assignment very confusing. Okay, but so if I said what is the stereoisomer of cis 2-butene, you would tell me trans 2-butene, right? Because that is a pair of stereoisomers. All right, so if anybody was a little confused by that assignment, I'm assuming it's because that key word was missed. Okay, cool. So cis-trans designation, we can do that for alkenes, but it actually only works for very simple alkenes. So let's take a look at another example here. Okay. All right, so are these the same molecule? Right, we want to convince ourselves because this double bond can't rotate, this is a different molecule. And this one, those fluorines are pointed on the same side. And on this one, the fluorines are pointed on opposite sides. And again, that double bond can't rotate, so there's no way for the one molecule to convert to the other. All right, so indeed, these are different molecules here. But this concept of cis and trans doesn't really apply anymore. Okay, so what the IUPAC gods, IUPAC is like what stands for the, what is it? I don't freaking remember. Anyway, it's this international organization of scientists that got together at some point and was like, look, we need to standardize the way that we name things, right? I can't be calling these molecules one thing, you're calling them something else, this dude's calling them something else. Nobody can talk to one another if we're doing it like that, right? So there's always been in the history of science this global push towards standardization so that science can be more global, so that we can have collaboration across the globe, right? So IUPAC is the organization that said, okay, this is how we're going to name organic molecules. Okay, so it's called the IUPAC naming scheme. So IUPAC came up with a way to tackle this problem right here by expanding on this concept of cis and trans stereochemistry and creating what's called EZ stereochemistry. Okay, so again, cis and trans works for the simplest of alkenes, but for more complicated ones, we can use this EZ stereochemistry designations instead. All right, so we're going to have a set of rules, like always, on how to assign EZ stereochemistry. Okay, so let's just take an example molecule here. Let's grab one of these. sort of illustrate each one of these steps as we're going. Okay, so step one, we're going to chop our molecule at the double bond. All right, so I'm going to look at this alkene here, and I'm going to chop it right in half at that double bond. Okay. So then step two, I'm going to look on either side and assign high, low priority. Okay, so we don't know how to do this yet. We don't know how to assign priority. But just to be clear, what I mean is I'm going to look on one side of this double bond here. I'm going to assign each of these groups either high or low priority. There's always going to be two of them, right? One of them is going to be the high priority group. The other one's going to be the low priority group. So how do we assign priority? Highest atomic number gets highest priority. Okay, so chlorine, fluorine, which one is the highest priority group? Of course we don't have a freaking periodic table in here. If we go to our periodic table, gotta have a million somewhere. Here we go. Ignore all this. Not our class. I'm gonna look. I got one of my groups is a fluorine. The other group is a chlorine. Which one has the higher atomic number? Chlorine. So chlorine is my high priority group. Where was it? All right, so over here, this one's high. That means that the other one is low. All right, so I do that for one side of my double bond. Now I'm going to jump across and do the same thing over here. Which one of these two groups is going to be my high priority group? Again, the chlorine. Okay, so then our last step here is E, means that the high priority are on opposite sides. So then Z means that the high priority are on the same side. So again, sort of analogous to the cis and trans designations, right? But now we sort of expanded upon that concept. We can do molecules where cis and trans no longer applies, right? So in this particular example here, is this the E or the Z conformation? This would be the Z stereoisomer because my high priority groups are on the same side, all right? Now, sometimes remembering the dumbest, stupidest little phrase will help it stick into your brain, all right? So in order to remember E and Z, which one's which, we can remember that the Z means that they are on Z, same side of the molecule. All right, how do we know whether it's E or Z? This one's Z because they're on Z same side, all right? Again, stupid as all get out, but that'll help it stick in your brain. Okay, so then E is then the opposite. Okay, so then going back to our previous examples, we can see that this, again, would be our Z isomer, and this would be our E isomer. And that's how we would distinguish between these two molecules here, right? Again, a pair of stereoisomers. Cis and trans doesn't apply because they're just too complicated. So instead, we have this sort of expanded way of doing our stereochemistry, E and Z. All right, so let's, we got to sort of do a little bit more complicated of an example here. We're going to name this compound here. All right, and to start it off, stereochemistry is going to be the last thing you do. All right, first you're just going to name it like you would normally name something. Okay, and then we'll worry about the stereochemistry at the very end. So everybody take a minute and name this compound for me, applying all those normal nomenclature rules that we've discussed. All right, so if I do my nomenclature correctly, I find that my parent chain is 7 carbons. I have a methyl group on there. I'm going to number it in both directions and see that this, like, what is that, left to right direction gives me the lowest number for my double bond. And yeah, so that makes my name 3-methyl-3-heptene. Okay, but now we have to make sure to include the stereochemistry. So for the sake of not making this too terribly cluttered, let me kind of take all these markings away. All right, so again, I'm going to look at my compound and I'm going to chop it at that double bond. I'm going to look on either side and assign high and low priority. Let's look over here first on this side. All right, I need to compare the two groups that are bound to this carbon right here. All right, so one of those is this, which is what atom? A carbon, right? We got this implied carbon here. And what's the other group that's bound to this carbon? Exactly, that implied hydrogen over here. Okay, I got to assign high and low priority to both of these groups. Which is the higher priority group, a carbon or a hydrogen? Carbon, right? So in terms of priority, this one's my high priority group, this one's my low priority group. Yes. Okay, now I'm going to jump to the other side of my double bond. But here, I'm running into a little bit of a pickle, because I'm going to compare this and this. And what are both of those atoms? Carbons, right? So this is a carbon, and this is a carbon. So how am I going to break this tie? Yeah, basically. So what we're going to do is we're going to list everything that's bound to those tied atoms. Okay? So in order to break tie, list all atoms bound to the tied atoms. So in this case, this carbon up here, what are its other 3 bonds? It's got a hydrogen, and a hydrogen, right? I'm going to list all 3. I'm going to do this in a different color so we don't get confused. Okay. And then over here, what is this carbon bound to? What are its other 3 bonds? It's got a hydrogen, but importantly over here is a carbon. All right, so then I look at my list here and I see that this is higher priority than anything on this list here. So that's what makes this carbon my high priority group and this carbon my low priority group. All right, and I guess just to be clear, got a lot of H's going on, so I'll just explicitly write low, high, high, low. All right, are these 2 high priority groups on Z-same side? No. So then it's going to be the E conformation. How we write that in our name is we put it out front in parentheses. Boom. So that would be the full name of that molecule, including its stereochemical designation.
Can you go back to the rules for
Yeah. Chop it at the double bond, look on either side and assign priority. If there's a tie, you're going to break it by listing the atoms bound to the tied atoms. And then E means that the high priority groups are on opposite sides, whereas Z means they're on Z-same side. All right, so let's just practice this. Do one more here. All right, so I found my parent chain, those 5 carbons. I found my substituents, a methyl group and a fluoro group. I numbered my parent chain, prioritizing that double bond. When I constructed my name, I put fluoro before methyl. Why is that? Alphabetical, right? When we stick it all together, we got to put it in alphabetical order. So 2 fluoro, 3 methyl, 2 pentene. Just rolls off the tongue. All right. Okay, so now I'm going to get rid of all these little markings so we can sort of more clearly see our next step. All right, so again, now I have to assign EZ stereochemistry. So if you have not already, take a second, looking at this molecule, chopping at that double bond, assign high and low priority on either side, and see if you can't tell me whether we're looking at the E or the Z stereoisomer here. Yep. All right, so I'm going to compare this group with this thing right here. And again, this would be a carbon, right? That's the atom that's bound. Fluorine or carbon, which one has the, I guess we got to look at a periodic table, huh? Fluorine or carbon, which one has the higher atomic number? Fluorine. So fluorine is our high priority group. And yes, you will be given a periodic table on the exam. This is our low priority group. Okay? When I jump across, now I'm comparing a carbon and a carbon, so there's a tie. How do I go about breaking that tie? I list all the other things those are bound to, right? So this carbon over here is bound to 3 hydrogens. This one is bound to a carbon and 2 hydrogens. So that carbon breaks my tie. So this is high and this is low. So then is that E or Z? Z, because they are on Z-same sides. So Z, 2 fluoro, 3 methyl, 2 pentene. All right. So again, I sort of said this when we started nomenclature. It's really about like the rules and applying that rules in this like sort of logical order. Good luck guessing that name, right? Like there's no way to like sight recognize these things, okay? That kind of works for the most simple molecules. As soon as we get even a little bit complicated, you got to go through that step-by-step procedure to construct the name, okay? Cool. So in the last little bit of time that we have here for this week, I'm going to just introduce the reactions of nomenclature. That doesn't make any sense. The reactions of alkenes. We will spend a good bit of time talking about sort of each category next week. All right, the specifics of the reactions, but just to kind of introduce them, they all have sort of the same basic framework. So again, if we're talking about reactions of alkenes, let me give you one such example here. Alkenes all of the reactions that we're going to study for our alkenes fall into the same bucket, right? The same class of reactions, what are called addition reactions. Okay. And I'm going to color code these carbons on either side of this double bond. Okay, so if I react, and this is just an example of one of the reactions, my product that I'm going to get now has a bromine on either one, on the carbon on either side of that double bond, right? So addition reactions we're going to be adding atoms to either side of our double bond.
Oh, you just forgot to draw in the double bond.
No, the double bond's gone.
Oh, it's gone.
The double bond's gone. The double bond has been replaced with a bromine on either side of that double bond. Okay, and it was Br2, so notice it was a bromine that I added on either side of our double bond. Okay, let's take this same sort of example, and I want you guys to try to predict, just based on what we've discussed thus far. We really haven't even done much, right? But just based on what we've done, by analogy, see if you can't tell me what the reaction between an alkene and hydrogen gas is going to be, H2. What am I adding on either side of that double bond now? Hydrogens, right? So again, the analogy kind of pretty straightforward. Instead of being a bromine now, I'm going to get a hydrogen on either side. Okay, what if I take this same molecule and I add HBr? Take a second and see if you can't predict what my products are going to be. All right, so same sort of idea, except for one side's going to get an H, the other side is going to get a Br.
Does it matter what side gets what?
In this particular molecule, it doesn't, right? Because if I had put it on the other one, I would have actually drawn the exact same thing. There is going to be a logic that we'll learn about next week as to what goes where, all right? It's a little bit more in-depth than the little introduction we're going to do right now. So you're absolutely kind of thinking ahead, and we will sort of have a logic. But for right now, it would have been identical. I kind of specifically chose this starting molecule for that reason. Cool, all right, so these are these addition reactions of alkenes, right? They're all gonna have this sort of same basic format where we're sticking new atoms on either side of the double bond, and exactly as was pointed out, we've lost our double bond, right? That double bond is what's involved in the reaction. It disappears when we get to our product side. I want to talk in our last few minutes about this particular reaction here, just real quick. This is what's called a hydrogenation. All right, and the reason I wanted to point it out is because I know that there are quite a few people in here who are like food science majors, right? So have we ever heard of a hydrogenation reaction before? Does that sound at all familiar? It's something that's used quite often in food production, in particular in like industrial food production. So like, you know, the big food conglomerates of the world. So an unsaturated, exactly, unsaturated fat would be something that looks, at least part of the molecule, right? Fats are these long hydrocarbon chains. Unsaturated fats are alkenes. They have a lot of double bonds in them, right? Unsaturated fats, those are the healthy ones, right? Cool. So what do our sweet companies, what do the little Debbies of the world love to use? They don't want to use this healthy crap, right? They want the saturated fats, which is when there are no double bonds, alkanes. Okay, those are the delicious ones. All right? It turns out that saturated fats are very common in animal products, but animal products are very expensive, right? So if I'm little Debbie and I'm trying to churn out a massive amount of these saturated fats, they found out that the easiest thing to do is to take a vegetable source, which is full of unsaturated fats, and just hydrogenate it industrially, right? Treat it with a bunch of hydrogen gas. And then I don't have to buy this expensive butter to get my saturated fats. I can just use this chemical process to convert cheap fats into my saturated source. Okay? So this reaction is used quite often. It's considered one of the like dirty ways of cooking, right? Is by using this chemical process to create this new kind of fat. But again, that's what the food industrial complex does, right? Figure out very cheap ways to make these sort of things. And so that this particular reaction, if you ever hear of a hydrogenation of a fat, it's referring to this process here, right? Breaking all those double bonds and creating just an alkane. Cool.